Good morning. Thanks for attending this online presentation, Subsurface Preferential Flow in Riparian Buffers. My name is Enrique Orozco-López, and I carried out this work with the help and advice of Dr. Rafael Muñoz Carpena and Dr. Bingal. Riparian buffers are ecotones between terrestrial and aquatic ecosystems along inland water streams. Riparian buffers are strips of natural or implanted vegetation that reduce runoff point source pollution by increasing infiltration and sediment deposition. Because of their dense vegetation and high biological activity, grass and forested riparian buffers have been widely used as a common control pollution practice to protect aquatic ecosystems from adjacent land use and increasingly for chemicals like pesticides. It is generally assumed that contaminant movement and deposition in riparian buffers mainly occurs in surface runoff. However, subsurface transport of dissolved contaminants can be significant in the case of nutrients and pesticides due to preferential flow. Preferential flow refers to conditions where the water channels through a small fraction of the soil profile. In our work, we focused on macropore flow because of their expected predominance in riparian bedded zones. Macropore flow occurs in large, continuous and structural openings in field soils, allowing fast movement of infiltrating water, solutes and pollutants. In addition, riparian areas, especially those located in lowlands, may be strongly influenced by a seasonal saltwater table, enhancing the impact of macropore flow. Riparian ecosystems are uniquely susceptible to macropore flow due to the intense biological and geomorphic activity present in them, such as detritic depositions, abundant roots, and soil fauna such as worms, molds, wombats, lateral pipe flow due to the strong hydraulic gradients with the descent stream, and the frequent and drying and wetting cycles. And therefore, soil macroporosity in riparian bedded zones is pervasive, relatively densely distributed, and dynamic. Prevalence of macropores in the riparian zone hasn't been studied yet, limiting the effectiveness of riparian buffers as a conservation practice. By quantifying prevalence of macropores in riparian buffers and integrating all the processes mechanistically, macropore flow will improve the prediction of riparian buffers performance. The objectives of the field experiments were to quantify riparian buffers preferential flow on an agricultural setting and test state-of-the-science numerical macropore flow models. Macropore flow has been typically described as a process with one or two flow domains, matrix and macropore flow. Single porosity models, for example, assume that the flow process results from the aggregation of matrix and macropore flow. Dual porosity models consider only macropore flow and the lateral diffusion with the soil matrix, whereas dual porosity models include matrix flow as well. From a particular pore size, capillarity in a porous media is not well expressed. And in kinematic wave approaches, only gravity drives water movement and is the foundation of the two selected models in this work. In the diagram, the two selected models and Richard's equation fall into one or more of these categories. Mimoso responsive model, for example, is expressed as a dual permeability model, but it is analytically solved as a dual porosity model that accounts for both capillary and kinematic. And Di Pietro et al. Kinematic dispersive wave is described as a single porosity model, which aggregating matrix and macropore flow. The field infiltration experiments were performed in an agricultural riparian buffer in Laikipia County in Kenya. First, 3 holes were dug in a transect of the riparian area to install the required soil moisture sensors at different depths beneath the corresponding plot. The sensors were each a composite of 4 segments with 60 centimeters length that were introduced horizontally, as it is shown in the picture at the right. This way, a dielectric grid allowed to identify and quantify macropore flow dynamics vertically. A rainfall simulator equipped with 4 micro sprinklers provided the necessary rainfall for the experiments. 3 infiltration experiments were performed in plot 1, the closest to the river, under dry initial conditions, and in plot 2 and 3 under wet initial conditions. Rainfall was applied at a rate of 5 centimeters per hour during 3 hours. Evidence shows that the activation of macropore flow is substantial under wet initial conditions, and therefore the 2 experiments under wet conditions were performed expecting macropore flow, in contrast to the dry experiment where macropore flow was not expected at all. The soil responsive model developed by NEMO in 2010. The traditional representative elementary volume approach given by Richard's equation assumes a sequential of advance of water. Unfortunately, this approach fails to predict the heterogeneous, non-sequential distribution of water flow seen in field experiments, both laterally and vertically. The soil responsive model accounts for this by assuming that the forcing factor for macropore flow at a particular soil layer is the water source, which is the rainfall and runoff, instead of being the soil layer above. This model foundation is the kinematic continuity equation, as we saw before, including a lateral transfer between domains. The analytical solution of this expression allows to determine soil water content as a function of depth and time, in which the calibration requirements are reduced to only 2 parameters: the capacity for preferential flow, M, and the characteristic travel time, TL. M represents the macropore internal facial area per unit volume that can support a flowing water film. The middle diagram shows an example of the capacity for macropore flow with depth obtained from a random macropore network. At the right of this diagram, we can also observe the active area fraction, F, in which the travel time is included. This parameter expresses how much area is having macropore flow with depth. In this work, parameter M is calibrated, whereas the travel time was set manually following NEMO's work. The basis of the kinematic dispersive wave is the kinematic wave model with no lateral transfer, in which Di Pietro included a new term to account for dispersion. Di Pietro described the hysteretic relationship shown between flow rate and water content by a non-linear relationship that includes 3 parameters: A, B, and V sub zeta. The combination of these 2 expressions lead to the kinematic dispersive wave. The kinematic dispersive wave was originally solved numerically by an explicit scheme. However, to enhance numerical stability, I solved this kinematic dispersive wave model using Crank-Nicholson's semi-implicit numerical scheme. The numerical filling of elementary volumes during an infiltration event is sequential with depth in the traditional kinematic wave model. What I propose is to non-sequentialize the solution by applying NEMO's idea of each soil layer responding to the water source. In addition, I propose to completely separate layers that show different responses by assuming that the outflow does not drain into the layer below. Also, layers showing similar water redistribution can be grouped to reduce computational efforts. This way, each layer or group of layers are conceptually connected to virtual preferential pathways instead of being connected to the soil layers above or below them. The 3 parameters in the kinematic dispersive wave can be calibrated at each depth if drainage, outflow, and soil water content time series from the soil column are available. However, outflow data are often scarce in field experiments, so the methodology consisted in simulating the flow rate with depth and time with a numerical scheme, and use the measured water content time series to calibrate these three parameters. The inconvenience of the Petro relationship is that when it is expressed in derivatives, results in Kini's equation, which shows convergence issues. Therefore, we proposed a new equation to ensure convergence and obtain the simulated water content explicitly, in contrast to the original formulation. Finally, the matrix of soil moisture time series with depth was calculated using the fitted set of parameters and the simulated outflow with depth. After applying the 3 hours of constant rainfall, we observed some water stains in the plots walls showing non-sequential macropore flow. Once dug behind the water stains at plot 1, I found 2 main roots of about 1 centimeter that were responsible for the observed phenomenon. Same applied to plot 3, where I found abundance of very thin roots, driving preferential flow to lower soil layers. Preferential flow evidence was consistently seen between 55 and 95 centimeters depth, with no macropore flow evidence in above them. Therefore, it was assumed that preferential flow patterns are relatively stable with depth and similar longitudinally across the riparian buffer. Before arriving to the field test, we compared predictions with the Petro benchmark data to check if it's equivalent. Figure A shows a very close match between the prediction and the observed data, and using the alternative equation proposed to account for the hysteresis, we obtain a close match with the observed data and the Petro prediction with some deviation at the downward slope. 5 out of 6 soil moisture columns in the dielectric grid showed signs of non-sequential macropore flow. Calibration of the 2 models was performed using data from plot 3. Responsive results were excellent, showing close matches with observed data in every layer except for the layer at 75 centimeters. Kinematic dispersive wave showed good efficiency at the upper 3 layers, although it did predict the arrival of a smoother wetting front than the observed data. Sensor at 95 centimeters depth clearly captured macropore flow. Sensor at 75 centimeters showed a slow water content response, which was interpreted as the influence of close macropore flow driving slowly lateral mass transfer. And in consequence, none of the models efficient was high at this level. The first test was performed in plot 3 and in different column than the calibration, and as expected, the results were similar than in the calibration. The second test was performed in plot 2 under the wet antecedent soil moisture conditions. So responsive still performed from good to very good in the upper 3 layers and from bad to very bad in the lower 2 layers, and kinematic dispersive wave followed similar patterns than those obtained during calibration, and since the plot was more broad than that using calibration, the efficiency was very poor. Finally, well, the main findings of this work, the abundance of macropore flow confirmed in the riparian buffer experiments performed in Laikipia, and importantly, evidence of non-sequential flow due to macropore flow was found. Not relatively stable macropore flow distribution with depth was found as expected. However, every macropore flow signal was found below 55 centimeters depth, which would coincide with the distribution and conveyance zone proposed by Ritsema and Decker and Kim et al. In 2005. So responsive and kinematic dispersive wave models show good initial capabilities. We applied in field macropore flow studies with a better physical description of so responsive than kinematic dispersive wave. Kinematic dispersive wave is dynamic, allowing for variable initial conditions of natural complex hydrographs. However, so responsive is based on steady state conditions, limiting its application to well-defined hydrographs. So responsive also lacks water resistant components, which is implicit in kinematic dispersive wave. However, so responsive is more parsimonious than kinematic dispersive wave model. Kinematic dispersive multi-layer implicit numerical scheme allowed for testing non-sequential preferential flow patterns. The model relies on the calibration of 3 parameters per soil. Depending on the number of horizons, this number of parameters can be high to achieve Froese inverse calibration results and requires high computational efforts. So responsive having only 2 parameters the travel time becomes a limiting factor due to the inherent complications of identifying the exact characteristic travel times occurring in a particular location. Macropore flow models capable of determining non-sequential multi-layer soil moisture independently at each layer will benefit decision support tools such as hydrological, agronomic, and water quality management models. For instance, riparian buffers design and management performance will benefit from a better description of macropore flow and transport processes through the riparian bed of zone. With the results obtained and future research recommended, macropore flow algorithms presented here can be integrated in a riparian buffer mechanistic flow and transport models such as BFS mod. Thank you all for your time.